Hello, good evening or good morning, wherever you are. Um, so welcome to our second Twitch live coding stream. So if you don't know what this is all about, the actual Grist platform has a short explanation, 20 minutes explanation in the first live coding stream, which is archived on the video. So we will basically go on developing our solar heating control system with the Grist board. What we figured out in the last stream was basically to make a new application and make a blinking light. And as I can show you, the blinking light is still working. Well, let me show you larger. So that's the Grist board. Random blinking light, random color, still blinks, and it actually it blinks since last week because I just left it blinking. So apparently the platform is stable. So we can rely on it like to keep running, which is a good feature for building a solar heating system. So let me get on the screen again. Desktop. Okay. So hello. Actually, the chat is quite quiet. Am I actually seeing this? Can you maybe say hi if you are online and watching this, so I can actually see you on the chat and see if it is working, or actually I can test it myself. Test, yeah. Test, yeah. Good, it works. Okay, so blinking light. That's actually the code for the blinking light here. So we are using a anonymous function which returns a random tuple between 0 and 1. So rand uniform that returns numbers between 1 and 2, and we subtract 1. So and that's what that's basically an RGB tuple, which then gets used into the put into the LED pattern. There we actually used hi Ttref 99. So we use this function in the Grist LED pattern function. We pass this function and an interval, and actually figured out this was undocumented. But we got a pull request for improved documentation in the meantime, and I will merge this soonish. So thank you for the pull request, Igor. We will. So the plan for today is, for one, to actually improve our development environment by actually hooking up the Grist board to the Wi-Fi, because at the moment we only have the serial console. So this is the console. You can actually see the Erlang shell is. So this is actually running on this board, but the console is not a very nice user interface, and it would be much nicer if you could actually do distributed Erlang nodes and remote shells. So we can usually I set up a remote shell to talk to the board, and a distributed loader node to actually remote load code modules. And once we've done this, which still this didn't get us any closer to the solar heating system, we actually want to try out working with a temperature sensor. So I got a few temperature sensors. So that is, I don't know if you can see this. Yeah, that's basically, maybe I should show the larger camera. Oops. So that's like a temperature sensor with like a steel cap and a cable and 3 wires coming out. And this is actually a 1-wire temperature sensor. And fortunately, we have a 1-wire interface on the GRISP board. And we will, basically after we set up our development environment nicer, we will try to talk to the sensor and then see how far we can get. Well, for now we leave this application and we will try to get to the on the Wi-Fi. So just as an explanation, that's the wrong tab. Let me get another one. So you can find a description of this, and actually at the moment not a code repository, but I will push the code repository to the GRISP repositories that we have here. In the GRISP repository, there's a wiki. Oh, actually, I'm showing just myself, so sorry about that. So let's try this again. So I actually wanted to show you, like in the GRISP organization, in the GRISP repository, there's a wiki where basically the first step, basically including, so we're basically already there connecting over serial. Now we connect over Wi-Fi, and then we're good to go to actually work on actual applications, except blinking lights. So first, to actually be able to do, I mean, the ultimate reason we want to connect over Wi-Fi is that we can do Erlang distribution over Wi-Fi. And to be able to do so, Erlang needs a program that's normally running behind the scenes, which is called EPMD, which stands for Erlang Port Mapping Daemon. This port mapping daemon is a program where all the Erlang nodes on let's say on your laptop that you started or on your server make a connection to the Erlang port mapping daemon, and if they can't find it, they start it. So the first Erlang node on the machine starts the Erlang port mapping daemon, and all the other nodes kind of connect to the port mapping daemon, and then they basically get a TCP/IP port number allocated by this port mapping daemon, which is the port they listen for Erlang distribution connection requests. And if you want to connect to an Erlang node on another machine, then you need an Erlang node name, and there's long and short ones. The node name always consists of a name part before the add, which is the local node name, and the host part, which is the host name. And you need to be able to resolve the host. Otherwise, you can't find the machine. And what happens basically when the Erlang distribution wants to actually talk to a Erlang node on another machine or the same machine, it finds out what the IP number is and then talks to the Erlang port mapper daemon, which listens on a well-known port. So it uses only one port, which like everybody knows, all the Erlang implementations. Talks to the Erlang port mapping daemon and asks about the node name, and then it gets answered back with the node number, and then it knows everything to actually do a TCP connection to the Erlang node, and that's how this works. So we have a slight problem here, because on GRISP, what we do is we boot the Erlang VM together with a thin layer library directly on the hardware. So we actually don't have processes per se. We only have threads, and everything is in the same memory image, and so we can't easily start a separate process. We have one simplification, and that is mainly that we only have one Erlang node. We know that on this machine, there's only one Erlang node. So we don't need to actually be able to manage multiple Erlang nodes talking to the same port mapping daemon. There would have been several workarounds for this. And back then, when I did the first port, I thought the easiest one would be to re-implement the Erlang port mapping daemon, which is a C program which has quite some history behind it. Let's say it like this. And basically the C program is not easy to port, and it has lots of like if-defs and all kinds of things in it. And I replaced it by re-implementing the Erlang port mapper daemon in pure Erlang. So basically, what's actually possible, you can actually use this pure Erlang port mapping daemon, run it on a non-distributed Erlang node on your machine automatically, and then it works like a normal Erlang port mapping daemon. But what we want to do, because we have only one Erlang VM, we want to actually run the Erlang port mapping daemon on the same machine, like in the same VM, sorry, in the same Erlang VM. And there's a few tricks necessary for this to be actually possible. So the first thing we need to actually do, we need to add it to our dependencies. So we go to, so our current directory structure looks like this. We have a rebar config on the outside. So this is our project directory. Then in the source, we have the blinking light source and the empty supervisor. And where we need to go is the rebar config file. So at the moment, what we see is our dependencies is only Grisp. Grisp is the only dependency, and Grisp is the application where all the Erlang level drivers live. So we need to actually add to the EPMD to the dependencies, so it gets fetched. And I have to cut and paste this because we actually need to fetch a certain Erlang hash here, a certain Git hash here. So we add to this list of dependencies a dependency called EPMD, and is actually fetched from GitHub Erlang EPMD, because I'm happy that the OTP team basically adopted my EPMD into the Erlang GitHub area. So it's kind of like semi-official now. I mean, the official one is still the one. Let me check the braces. So, and we need to get the special reference because the one on the Erlang GitHub is there are some changes made that actually breaks it for our use case. And to be honest, we didn't get around actually fixing it, and just picking an old version which has exactly what we need apparently worked too well. So now we fetch this version of the port mapping daemon, and now we need to add it to the release also. So in the release we only have our project name, so G for Grisps, Solar, System Control, whatever. So, and we want to actually load EPMD, but we don't want to start it, because normally every Erlang application in a release gets loaded and started. EPMD we don't want to start, because we actually need to start in a special way. And I'll get to that. So none means basically load this, but don't start it. But make sure it's loaded. It's part of the application. So and we will get later to the part where how it actually gets started. So what we in addition need, we need to actually make sure that the name resolution for all the for the names, because we don't have a DNS system set up, and I want to make this work wherever it is, just by IP numbers easily. And there is there's a nice feature in Erlang that you can have an inets configuration file, which lets you specify all kinds of like host file values and not depend on the operating system, which is very convenient if you don't have an operating system. So there is, actually at the moment there is not. There's basically, we defined a special subdirectory tree in every application, which is like added to a GRISP repository, which gets, where we have files which get compiled and collected together when we make a release. So what we need to do is we actually need to make this because we don't have it yet. So the subdirectory is GRISP. So all the GRISP related stuff goes there. And then there's a subdirectory for the actual platform, the hardware platform, because we already planned for having multiple one. And so in this case, it's GRISP base, which means, which is the official name for this first board. It's called GRISP base. And then we have a subdirectory called files, which basically is extra files which get copied on the SD card. So it basically collects everything that it finds in all these files directories and copies it on the SD card in addition. So this lets us basically keep this automatic, because as you have seen in the last stream, it's quite convenient that we actually, if we do a GRISP deploy, we copy all the files and all the release parts on the SD card, and basically, so we can actually erase the SD card every time, and this gets automated. If you would have like a manually put file there, we need to be very careful that we don't overwrite it. So we make this directory, and what we want to do is, we'll do this in the editor. Nope. GRISP space files. So we want to have a file called ERL, like Erlang, inets, which is the name of the application, RC, which is where you can configure things, which is kind of like dependent of, and let me just copy a template there. Save some typing and not make any mistakes. So that's basically a template for Erlang initclc. So let's put Erlang mode on, so that gets nicely colored. Oh, this line is too long. So what we can have here is we have host, a list of hosts, which basically is an overriding of whatever. That's basically the first thing it looks at. If it finds anything here, it actually looks it up. So there's an IP address in tuple format. This is the XXX, so we put IP addresses there, and the host name. Here you can actually tell it where your host file would be. So you could actually have a etc. host style file here. And if you, which it actually would use by default and try to use by default. But here we basically say host file empty string. So don't look at the host file because there is none. And we don't cache anything. It doesn't make sense anyway here. And we basically specify the lookup method, which is file native. That would be the order. We first look in the file and look at native. But we disable the file, and native doesn't exist at the moment. It's not configured. So it would actually only look at the hosts part. So what we need to put in here, so this gets copied on the Erlang on the Erlang node, and what we need to copy here is the IP address of the development host. So of this machine I'm actually on. So let me see what the what the IP address is. Well, there's lots of IP addresses. I probably don't want to share all those. So it's 192.168.90.6. Actually, I would have known this by heart. So 192.168.90.6. And we basically give it the host name, and this one is called URL because it's the name of my host. Actually, it helps if you put the actual host name there. That is very useful. So now when the GRIS board starts and we point it to this Erlang init rc, it can actually figure out what the IP number of a host named URL is. And that's all we want to achieve here. Because for Erlang distribution to work correctly, both ends have to actually find each other and be able to resolve their name, their respective name. So that's fine. Then there's another file which we also need to copy on, but that's a little bit more complicated because it's actually a template. So we have a templating engine in the build toolchain. So we still again go to files. So now we should actually see our init.rc. And what we want is a file called grisp.ini. So this is actually a default file which gets generated and put on the SD card by default because it's kind of like crucial to boot on the system because the bootloader looks there to find the actual image path, and the Erlang arguments come there, and then other things can happen. So you can configure all kinds of things there, which need to be configured before the actual Erlang VM starts. So we call this file with the ending mustache because that's the name of the templating system. So this is a mustache. Mustache is a templating library that we use here, where you can actually replace, and I save some typing by actually cutting and pasting this out of our wiki article. So this is actually, you can actually follow this easily by just copy and pasting from the wiki. So this basically, the boot section is looked at by the bootloader, and it only has one entrance. That's the image path. That's the mount point. The first thing is the mount point of the SD card. Then this is a templating thing. The release name gets inserted there because normally a Erlang release gets put in a directory of the same name. And then there's basically subdirectory ERTS and the version of ERTS that we're actually creating. And in the bin directory, we expect to find a beam.bin, which is the actual image file, where the bootloader can find the Erlang VM linked together with OTEMs as a raw image. So it basically loads this raw image into memory and jumps to its beginning, or to a fixed pointer, I think. And by having these mustache things in there, this line basically is a copy of the default line that's built into the GRISP toolchain, into the Reba plugin actually. By copying this, we make sure that we always have the right release name directory and release version without having to adopt it all the time. And then the arguments are a little bit extended. So that's the arguments to the actual Erlang VM. That's the name, which is not important. Home directory is the current directory. We make sure that the current directory, the home directory, like basically the thing where it's actually booted from, top level of the SD card, is also in the path. So we can actually throw a beam file there, and it would actually be able to load it. Then we need to tell it where its release root is. That's the root thing. And there we put the release name again, because that's the directory. And then the boot argument is basically going into release name, releases, release version, release name. That's the standard path where the boot script is actually put. Oh, actually, I'm not plugged in. I'm so sorry. Sorry for the bad audio and for the click here. So let me tune my audio. So yeah, I think it's better. So I wouldn't have needed to wear this because I was not plugged in. Sorry about that. So the boot script is a file that is initially read by when the Erlang VM boots, and basically it tells it all kinds of things like load this file, load that file, do this, do this, configure this variable. So the boot script is how the actual beam boots, which is already working. So the boot script is already read by a piece of code that is written in Erlang, which then uses the prim loader to actually load the initial beam files before it actually has the actual code loader. And the prim loader and all these special Erlang files are baked into the image. There's a special feature to bake it into image. Then this is a new option which you would not find in the documentation. Internal underscore EPMD, EPMD underscore supervisor, or SUP. So the thing is that this internal EPMD can't be started as a normal Erlang application because it needs to be started at a certain point when the net kernel boots up, which is the part of the kernel that makes distributed Erlang work. And we need to make sure that the processes consisting of EPMD get started before the net kernel wants to actually talk to it and connect to it. And this option basically inserts it into our patched net kernel, which looks at this option and adds whatever module is there into the supervisor of the net kernel, so it in the right point, so it gets actually automatically started. Then the next option is kernel, so it wraps a line. Sorry, kernel means that this is a environment, an application environment for the kernel application. So minus kernel means like, yeah, this is for the kernel application because every application has their own environment. And there's a variable inetRC, and we point it to our current directory, inetRC. That's where this inetRC file goes, which we just edited. So this one. So actually, this is the Grisp ini we had put on, which we initially put on the SD card. Actually, why is this in source? I don't know. We'll see how this works. And then we had a network section which is also not in the normal Grisp ini, or actually just disabled. We configured that our IP address is actually requested by DHCP. So we assume there's a DHCP server and not a fixed IP address. We enable the VLAN, the Wi-Fi chip, and we need to actually pick a host name here, which usually I don't call my Grisp board, but I call it the board and the serial number. So let's have a look. If you look at this, if you look at the table, there's the sticker and there's a serial number. I think you probably can't read it, but I can't read it. And this is serial number 200 because I picked a board with a nice serial number here. So to be able to easily talk to multiple Grisp boards, I usually call them Grisp and then the serial number. There's 3 digits, so I always know how it's called when I look at it. So that's it. That's our mustache file. So we also need to add another line to the Wi-Fi configuration because my Wi-Fi is encrypted. So we need to make sure that that a ported thread called WPA supplicant, which exists on Linux and FreeBSD also, and we have a ported version to Artems which runs in a thread. And if you configure this, it gets started and it expects its config file, which is the same config file as on FreeBSD, by the way, because we're using a FreeBSD network stack actually. And then we need to provide the WPA supplicant thing config file. And we also put this in files. And so we expect this to be called WPA supplicant.conf. So empty. So now this gets interesting. Let me copy a little template here. So that's the template. So usually key management, WPA, PSK, that's the thing that you always have. You need to put the SSID there and the actual password of the VLAN. So I actually don't show you my WPLAN password. I mean, I work on the countryside and it would not be so easy to actually hack into my Wi-Fi. So 1 second while I get my password out of my password save. I don't show you this either. Doesn't work. 1 second. No. Now I got it. And add the SSID. So now remove the file and now we're back. So the thing is I added my Wi-Fi password basically. Actually I made a mistake. 1 second. Let me try this again. I have the wrong SSID. And remove the file again. Okay, so now we're back. So we have a Wi-Fi password in the right file, and then actually we can make a new version of the SD card. So for that we need the SD card, which you get from the thing. Put it into my reader slot here, and I probably have the crisp deploy. So that's how we make a new SD card content for those who didn't watch the last thing. Now you see it fetches the EPMD and it builds it, and it uses a precompiled OTP. Now it copies the release, which takes some time. Running PostScript, which ejects the SD card, so we actually can get the SD card, plug it into the grist board, watch the console and see if we did it right. So now it boots. Setting up Wi-Fi probably worked. So that's successfully initialized WPA supplicant. That's good, and it tries to connect with my Wi-Fi address on this frequency, and it's associated. So this worked. Key negotiate apparently worked. It's connected. That's an error you can ignore. And now we need to wait until the actual Erlang VM starts, which, as I said last time, is kind of slow. So that's not good. So we got an error message. inet config file not found /l inetrc. So but we actually put the file in our files. So what happened? Typo in the file name. So let's rename this. Because it's inetrc and not inetrc. Okay. So this was in vain. Actually, what we see here now, what we actually reached is that this is well, actually we can save one step here, so this is not lost. So we have a node name, which the default node name is always the name of the release. So the name of the actual release we built, and the host name is the GRISP200, which is the host name. So what we still need to figure out is like what IP address was assigned to the GRISP board, and let me see if I remember this right. Nope, that was not right. So let's look at the documentation. So that was the function get interface address. That's the one we want. So inet get ef address, no argument, and that worked. So that's basically what you would get when you do if config on a Mac or FreeBSD box or ipconfig or one of the newer ones on Linux, but on the Erlang level. So we learn here that we already got an IP address, and that's the 224. So we need to remember this because our host needs to learn that this is actually a host called GRISP200, and there's two ways to actually do this. One easy way is to actually add it to your etc hosts. So I actually need to kind of, let me see if we have one. etc host. So there is localhost, that's the usual empty etc host. I mean, probably not allowed to write this. So we need root. And we just append to etc host. Don't overwrite your etc host. Make sure that you have the double thing here. We append to it, and basically the format is IP address 168.90.224, and the host name is GRISP 200. So, oops, I hope I didn't mess up anything. No. Oh, there's a Pico. I could have used that right away. So, looks good to me. Okay. So now if I want to ping my new machine, this should actually work. So I should be able to ping 192.168.90.224. So yeah, we are on the Wi-Fi. And now I should also be able to ping GRISP 200, which also works. So my lookup works, so Erlang will be happy. So the only thing is we need to actually fix our Erlang init.rc, because our Erlang node wouldn't know how our development host is named, which it doesn't like very much. Sometimes it works, sometimes it doesn't, so that's not so good. So we fixed our file naming problem. We get the SD card again, put it into the Mac. Actually, how are we doing on time? Oh, 45 minutes to get on the Wi-Fi. Well, but I'm talking a lot. So we do the GRISP deploy again. Our prescript always erases the whole SD card, which makes it possible that we get a clean slate. Now it's ejected, put it in again, and reboot. So in the meantime, we can actually have a look at the wires coming out of the sensor. So we have I don't have documentation for this. These are cheap, probably Chinese-made sensors off of Amazon. Probably for the actual heating system, I will use more expensive ones, which might be nicer and more robust. But for testing, this is fine. So we have a can you actually see this? Let me check to hold it right in the middle. We have a black, a red, and a yellow. So one wire actually uses only one wire, which is a lie, because you always need ground also. So it's two wire already. And we use a variant where we also have a power wire. So assuming that the colors make sense, we will find out if they make sense. Black will probably be ground, red is like VCC power, and yellow is the signal, which is one wire only, at least. At least the signal is only one wire. So we will try to hook it up to the GRISP board, where I also have to figure out how the pin out of the one wire connector is. I hope we have documented this somewhere, so otherwise I need to dig for it. In the meantime, we are still connected to the Ethernet, and we have our node, and we have no error now. So now we can try. Let's start another terminal. So now we can try to run an Erlang node. So actually, do I have the right Erlang version as default? Yes, it always helps. So I want to go to the project directory so we can actually find files if we want to hotcode load or whatever. So what we do want to try is what we want to start a remote shell to the actual Erlang node, to the grist board. So you always need to give the remote shell also a name. So I call it R1 for remote shell 1. And then there's a special argument remote shell, and then you give your target. So this is so control at grisp 200. And now, not good. So connection attempt from disallowed node R1 iRail. So it actually worked, but we were not allowed because we forgot about the cookie. And I think I left the cookie on the default. So let's look at our Crisp ini. So we left the set cookie at my cookie. Well, that's a pretty stupid cookie, but since I don't want to boot new, we can actually just do the same here. My cookie. And then it should work better. Let's see. Well, that worked. So now in this terminal, which runs on my Mac, we have a remote shell over Erlang distribution over the Wi-Fi to this grist board on the table. So I can prove this by doing grisp led set led 1 and then 0 0 0. And if I got this call right, I would expect not, oh, undefined. Oh, let's look at the documentation. We have no idea what we're doing. So the grisp modules are actually documented under hexdocs. So in hexdocs you have all the documentation API as far as it goes. If you miss anything, pull requests are welcome. So we have a function called, oh, there's a function off, crisp led off, flash is flashing, and color sets it to a color. So let's just try to switch it off. And off takes one argument, which is the number of the LED. Let's see if this works. And as you see, only one is flashing. So let's kill this too. They're all gone. And this works over remote shell. Hi Adam, too many quotes maybe? Did I do quotes somehow? I don't know. It's probably an old comment, sorry. I think I just plow on because it kind of works now. So we have a remote shell. What we also can do then now to set up our nice development environment, to have another, oh, not so large, don't overdo it, to have another terminal, or actually make this another terminal tab. I mean, the built-in terminal has terminal tabs. So we do another tab here. Oh, that's interesting. Oh, that's actually a subshell. That I don't like this. I want my profile to work. So they're all init.rc name. Yeah, we had a problem with the init.rc name, but yeah, it was just a typo in the name. So yeah, thanks anyway. Sorry. Actually, Wanted to look more at the comments, but I'm still slow. But there were not too many comments today. So we go in the directory again because it doesn't hurt, and we give this a name. I often call this loader because it's my loader node where we can actually do hot code loading, and then we also need set cookie. My cookie. Should pick another cookie name. But I mean, cookies are not a security thing anyway. So this is now a local node, loader at URL, and then they kind of do a net ADM ping. So control at grisp 200. Oops, not 2000. Didn't. Pong. So this works. So we can actually do netload here. So netload is a nice little thing that if you, let me show you. Let me just show you. So let's hack something. So that's actually, I should actually have gone to the source directory. Because that's where you usually go. So with the loader, you go into the source directory. I mean, this is a little bit hacky, but it's super useful. And then you do your remote shell, net ADM, ping. Should have picked a shorter name for the application. Grasp, oops, 200. So, oops, well, net minus ADM ping doesn't work. It's, of course, it's an underscore, pong. So, for example, what could I show you? Well, I don't want to reload the application file. Let's just introduce a new file. So, in our source directory, we would have this file. Let's introduce a file test.rl and sorry about the export all, but I'm too lazy and it's just a try. So now we do a function foo which returns, what do you guess it returns? Bar? Yeah, bar. Okay, so I made a little module here, a very minimal module, and if I go in my loader shell, I can actually compile this module, I hope. Compile test. Yeah, warning, export all flags enabled. I mean, it's good that the warning exists, but yeah, I know. I could have actually switched off the warning at the same time, but it kind of like defies the thing. I think I should suffer a little bit for having export all on. So I compile test, so I have a beam file there. And also, it would have loaded it into no local node. But what we want is that it actually shows up on the Grisp board too. And so normally if you build a thing like also with rebar compiler or whatever, and you load a file, there is the L shell command, but there's also NL. NL means netload, so which means load, let's show you the nodes, load this module into all these nodes, which is also our remote shell, but it doesn't hurt unless you overwrite the remote shell code, which would be funny actually. And onto our Grisp node. So if I do a netload test, I would expect this module to actually show up everywhere. So I locally could call test foo, need to test our foo, and it returns bar. And now I go to the shell, so you actually by color see that we are actually really there, and we should be able to call test foo and no argument, and it works too. By the way, the double echo here, that's a peculiarity of the shell, which is one of the reasons we actually want a remote shell, and we want to try it out in the remote shell too, which is not like we're not running the test module that we by accident also loaded into our remote shell node, but we are connected to the shell, to a remote shell on the Grisp node. So when I call test foo, it actually runs on the Grisp node over the Wi-Fi, back to the Wi-Fi, and we get the result. So this is pretty nice already. We have a nice developed environment, and there's probably no time to actually do much more today. So what did we do? In the last stream, we basically made a. Actually, we should switch on the blinking light again, just to show off that this still works. Flash. Let me look at the documentation. Position, color, interval. So LED 1, color red. I think red works for colors. And interval like every 100 millisecond. And also let's flash LED 2 in green. Even faster. Oh, interesting. What did I do? That's an interesting crash. Grisp LED init. LED not found 3. Oh, yeah. Well, I agree. LED 3 doesn't exist because we only have 2 LEDs we can talk about. But I kind of crashed. I crashed the Grisp supervisor. Well, I'm not sure if we cleaned this up right. The question is, does it still work? Oh, it restarted. Erlang is great. We triggered a bug because it's kind of a bug that the whole thing crashes if I pick a wrong LED number, 2 instead of 3. But it was restarted and everything is fine. My node still rested. I can still flash it green. Of course, we forgot its state. Now they both flash red, but both red is boring. Blue. Now I want blue. And I want the blue faster, please, than the red. Yo. So let me show you the table camera. So yeah, that's what you get from Erlang. It basically crashes, but it works. Cool. Works also in embedded systems. And we can remote load modules over the Wi-Fi, which will be super useful because if you imagine what kind of workflow we had to do in embedded systems development, and I remember very well, like before we had systems like this, is that you hack your C code, you compile your C code, you cross-compile your C code, then you have a expensive box called JTAG debugger. You load the code with the JTAG debugger in the flash or in the RAM. You reboot your system, then you trigger a bug and your system crashes. You possibly don't get any information. Yeah, nice accidental demo. I agree. I didn't plan for this. So you load with the JTAG debugger, which sometimes takes minutes. So this is not a fast process, load by JTAG, if it's a larger program or a slow JTAG. And then you crash, and then it doesn't work, and then you need to do it again, and you start in the debugger, you set a breakpoint, it crashes again, and you took forever until anything works. And what you now can do is actually we can play in the shell. We can play in the shell with hardware. We can like talk to hardware registers directly from the Erlang shell and play with hardware. So because often you just need to figure out how the hardware works. And then we can actually copy this, what we learned, into a module, and we can hot code load over the network, over the Wi-Fi, the module on the actual board. And I still remember the point like years ago when I figured out that I had this like embedded system where I was developing a device driver for an RFID system, actually, for a customer. And this was running Erlang, so we built a RFID system running Erlang on a similar node than the Grist board, but a different CPU, PowerPC CPU. And I did not reboot my node, my embedded node, for 3 days. But I was working 3 days on it, like I was editing my code, and I basically did not manage to crash the whole node, because I only crashed. Of course, I did a lot of those crashes that we had in the blue window here, but it never happened in the whole node. So I think this wraps up. We have a 1 hour time limit kind of like set to ourselves to drag this not along too long. So next week we will be online again, same time. And please join us, and please like send on the channel, because the Twitch channel is much more fun if you have much more people watching. Next week we actually hook up one-wire temperature sensors and try to read temperatures, because reading temperature is kind of essential if you want to build a whole solar heating system. Maybe I have some time to actually explain a little bit how the solar heating system works and how it's not wired but piped together, and where do we plan to put temperature sensors, and how do we actually then control it. So it's no longer manually controlled as it is before. So thank you for your time. Thank you for watching. Hope to see you next week. And distribute the link. There will be a video archived right after this today evening, where you can actually watch the whole thing again. Yeah, thank you, ttref99. And also have a nice day. Well, actually, you have a whole day because you're there this morning in LA. Nice to meet you. So, and bye-bye everybody else who has been quiet on the chat. Also bye-bye Adam, and thank you for helping. Okay.